Okay, question number 3. Fuel producing bacteria or fuelomycins. So, the skeletal formula of cyclopropane is shown above. Determine the molecular formula, very straightforward to start with. That shouldn't be any trouble for us at all. So, if you don't know skeletal formula, it's definitely something you want to learn before taking the Olympiad paper. So this is going to be C3H6. Then we have a Hess's law calculation. So you're given all this. It's quite nice. So they're going to compare cyclopropane with cyclohexane. So cyclopropane, as we've just seen, is C3H6. Cyclohexane is C6H12. So cyclopropane, cyclohexane. And the idea is that even though they've both got the same empirical formula, which is CH2, this is going to be a better fuel because it has this ring strain in it, which means that it just reacts more vigorously, it releases more energy because of the strain in the ring. Obviously, you've got these 60-degree bond angles, which are not ideal. So, write the equation for the combustion of cyclopropane. If you can't do that, you might want to reconsider whether or not doing the Olympiad is a good use of your time. So we have that 3 carbons, 3 there, 6 hydrogens there, and then we've got 6 oxygens, 3 oxygens. So we have that. Obviously they'll accept any multiple of that, so if you want to multiply everything by 2, that's fine. Then calculate the enthalpy of formation of cyclopropane. So we want to know the enthalpy of formation of this thing here. We're told that this reaction, which is the combustion reaction, is minus 2091. So I'm just going to write here minus 2091, and then I know that that is going to be equal to the enthalpies of formation of the products minus the reactants. So it's going to be product delta HF minus reactant delta HF. Okay, just straightforward Hess's law. So then I can write that in. So my products, I'm told, formation is 393.5. So it's going to be 3 times 3. Let's get this carefully. 3 times minus 393.5 plus water. 3 times minus 285.8. And then it's minus the enthalpies of formation of these two. So minus, and then this is the one that I'm trying to find. I want to know the enthalpy of formation of that. So I'm just going to call that X, plus 9 over 2 times enthalpy of formation of oxygen, 0. Okay, and then I just solve that equation for X. I've done it kind of not very neatly, but you get the idea. So if I do my minus 2091, and then I'm going to bring these over. So this is negative here. I bring it over, I add it on. So it's going to be plus 3 times 393.5 plus 3 times minus 285.8 gives me minus 53.1. This is where most people are going to lose this mark here. They're going to be like, calculator says minus 53.1, but that's not okay because it's minus X. So what I end up with is minus 53.1 equals minus X, or X equals 53.1 kilojoules per mole. All right, please don't make that mistake. Part 3, calculate the enthalpy of combustion per mole of carbon per atom. Sorry, start again. Calculate the enthalpy of combustion per mole of carbon atom for cyclopropane. So cyclopropane is 2091. There are 3 carbon atoms, so I divide it by 3. So 2091 divided by 3 gives me 697. Now it says the enthalpy of combustion per mole. So combustion is going to be negative. So it's going to be minus 697 kilojoules per mole. And then it asks you to do the same for cyclohexane. So that's going to be minus 3951 divided by 6, which is minus 658.5 kilojoules per mole. So you can see, even though they're both got the same molecular formula, sorry, same empirical formula, giving the same products in the same ratios, you get more energy when you do it per carbon atom when you use cyclopropane. All right. So that's the end of that Hess's law part. There's always a Hess's law question in the Olympiad. So if you don't know Hess's law, or if you haven't gone over it in class yet, it's really something that's worth your time going through. They won't be as kind as they will be in your normal school exams. It'll be something a little bit more tricky, but it's the same basic chemistry. So then we have to use cyclopropane as a rocket fuel. And we want to use this weird looking thing here, which has got 3 cyclopropanes in it. And we are now into enolate chemistry. So if you are interested in organic chemistry, or if you're interested in getting a very, very good score on the Olympiad, enolate chemistry is something you might want to spend a little bit of time reading about. It's pretty important, and it covers a few different things like organic synthesis and resonance structures, so it's quite nice. So, draw a resonance form of the enolate intermediate. This is the enolate intermediate. A resonance form is just going to be formed. This negative charge, here it's on the carbon. Obviously it could go up and do that, which would give you this. Okay, hence the name enolate, because I've now got the ene, which is the alkene here, and the ate, which is the negative charge on the oxygen. All right. Then, in the answer booklet, tick the correct statement about the reaction between iodomethane and the enolate intermediate. So this reaction here. So this step here. Right, well, it's kind of difficult to answer this question without knowing a little bit about how the reaction works. So what's going to happen is, if I just redraw my thing here, and then I've got CH3I. So I'm basically going to add this methyl onto this here. You can see the carbon chain gets longer. Here I've got 1, 2, 3 carbons in my carbon chain. Here I've got 1, 2, 3, 4 carbons in my carbon chain. So I'm just going to add this methyl group onto here. And the way it works is the electrons come down, reform the ketone that I have in my final product. And then, now this is going to be a little bit tricky because I could just do the arrow straight from the double bond, but you might often see it drawn like this, where it goes through the carbon that's going to be reacting. Because if I just go straight from the double bond, is it this end of the double bond or is it this end of the double bond? All right, so I'm going to do it like that, and then that is going to kick that out. All right, so you should be able to see the electrons are moving from here to here, which means that this is the nucleophile and this is the electrophile. So the enolate intermediate is the nucleophile and the iodomethane is the electrophile. There's no acid-base chemistry here. There's no proton transfer, so we can just ignore those last two. Reducing agent and oxidizing agent. There is an argument to be made here because this is the nucleophile. It's donating the electrons, and if you're remember, reduction is gain. So this is giving the electrons to this. So this is making this gain electrons. So this is reducing this. So you could be tempted to tick this one here. It does say, it does this thing here where it says statements, suggesting it could be 1 or it could be 2 or it could be however many you want. But the mark scheme kind of quite helpfully says that to get the mark you need to have the fourth top box ticked. Okay, if you do tick the first box, you will still get the mark as long as the fourth box is ticked. If you tick the first box but you don't tick the fourth box, you don't get any mark. Alright, so they're okay with you thinking about it in terms of reduction and oxidation, but really it's a nucleophile-electrophile reaction. Alright, enolates can also react with a carbonyl compound as shown below. Draw the structure of compound A, which is formed as an intermediate in this reaction. So, what's happening here? Well, molecular formula. So the molecular formula of this here is C3H6O. Oh, and the molecular formula of A is just twice that. So these are two added together. Now, if we've understood the way that this reaction worked, we can understand the way that this reaction works. So instead of my enolate intermediate in this form, I'm going to redraw it. Oops, not like that. I'm going to redraw it like that. I'm going to try and draw it neatly, like that. And then I'm going to draw my other one next to it, and then it's going to do the same thing. Okay, so this is the nucleophile, which means that this is the electrophile. Now, the nucleophilic attack will occur at this carbon center here. All right, because it's bonded to the oxygen is more electronegative, which means that it's drawing the electrons away from this carbon here. So this is an electrophilic carbon. All right, so I'm going to do the same thing. I'm going to come down here, get there, and then that's going to go up there. All right, which is, if you follow everything through, I'm going to have my ketone. This carbon here is this carbon, obviously, but it's now bonded to this carbon. Okay, so this carbon here is this carbon here. And that is bonded to the oxygen, which has now got the negative charge on it, and two methyl groups, like that. Okay? Now, that's not going to be, the formula of this is obviously not going to be C6H12O2. So this is then going to form an alcohol. All right, it can't form a ketone because I've now got three carbons bonded here, so it's going to form an alcohol. So I'm going to get this product. Okay, now this is an interesting bit of chemistry. They don't name it, but this is an aldol reaction, if you want to look it up. The reason it's called an aldol reaction is because it forms an aldehyde alcohol. Aldehyde alcohol. Now, I know this technically isn't an aldehyde, it's a ketone, but it's the generic form. You know, this R group could be anything here. So if you want to read about it, then the aldol reaction is what you need to look up. Okay. So then we have further steps in the synthesis. So determine the structures of B to E. All right. So B, fairly straightforward. So I'm given the molecular formula of B, C, D, and E. Very helpful. So the first thing I want to do here is work out the molecular formula of this. 1, 2, 3, 4, 5, C, 5, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and O, 2. So all I've done is I've replaced one hydrogen, one oxygen with a chlorine. So I've got rid of the OH group and I've put a chlorine in. So let's not think about it too long. That is B. Okay. Then C. So what's happened here? I've gone C5H9ClO to C5H8O. So I've got rid of an HCl. Okay. So if we look at this, how are we going to get rid of an HCl from here? Okay, so this is where it starts to get a little bit tricky, and this point now is when, if you haven't really been thinking about the question up until this point, then you're probably going to have a little bit of trouble, because this is where the enolate chemistry starts to come in, because we were told earlier on, so it relies on enolate chemistry. So we should expect enolate chemistry to come up here somewhere. And it is when the carbon next to a carbonyl group is deprotonated. Okay, so what's going to deprotonate it? Probably a base, which is what we're reacting with here. Okay, so this is a little bit tricky because, let's see if I can fit it in here. If I take my B, take B here, this thing here, and I form the enolate of that, which is going to be that. Okay, now we had earlier on two different examples of the enolate reaction. So we had this example here where we reacted it with the iodomethane, and then we had this one here where we reacted it with another ketone. But now it's getting tricky, because what's happening now, it should have become obvious at some point, is that in order to form this ring, this is going to have to react with itself. So this comes down as before, and then we get this reaction here where this carbon bonds to this carbon, and that will form a 1, 2, 3 membered ring, and then the chlorine comes off. Okay, so then let's just draw that product out. So that bit's easy, and then I come down to this carbon. Now this carbon is going to be bonded to this carbon, and it's now bonded to this carbon, which is also bonded to that one. Okay, so that is my product C. Okay, so that one, pretty tricky. All right, then D. Okay, so to go from C to D, I've gone C5H8O to C10H14O. Carbon number is doubled. So basically C must be reacting with itself. So this is reacting with another one. All right. So let's have a little think about what that reaction might look like. So if I let's do it like this. All right. So first thing I'm going to do is draw my enolate form of intermediate C. So now I guess you could form the enolate on the other side by deprotonating here. You'd have to think about which proton is going to be more acidic perhaps, and the stability of the double bond. I don't want to get into, you've got a very tight time limit, all right? So if you're looking at the product here, I think it makes more sense if I'm reacting it with this. Okay, I can already see that the reaction of these two things here kind of looks like this over here. Yeah, I've got one cyclopropane on this end. I've got one cyclopropane on this end. And then I've got my two carbons in the middle. All right, that's going to be that carbon. Well, will I have two carbons in the middle? Well, let's just do it and find out. All right, so if I bring that down here, and then, oh no, I'm going to have three carbons in the middle, but that's okay because I'm going to have three carbons up here as well. Ooh, tricky. Okay, so then that's going to go, oh, I should have gone through the carbon here just to be consistent, but never mind. All right, so then I'm going to get, so this carbon is this carbon. This one here. I should use another pen. This carbon is this carbon. This carbon is this carbon, which is bonded to this carbon. And that is bonded to that, and that, and that. Okay, which at this point you should be fairly happy that that's the way the reaction works, because if you compare what I've got here to my final product, you can see that this middle ring here is going to form from the reaction of this carbon and this carbon, and then I have my little extra methyl group sticking out. Alright, so we're on the right track. Now, if I do what I did before, where I just replaced that with a hydrogen, then let's double check with the molecular formula. So I've got 3, 4, 5, 6, 7, 8, 9, 10 carbons, C10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hydrogens and 2 oxygens. But my target molecule for D is C10H14O. So I've got to lose H2O, all right, which means I'm going to have to do an elimination reaction. And the elimination will just be the removal of the alcohol. All right, so if I remove the alcohol, then my product D will be so when I remove the alcohol I get the double bond, all right, and then I have, that's my, that one, and then I get that. Okay, so the difference from here to here is just that I removed that OH, I've removed that H, and I've made the double bond here, and then I've just, to make it neater, I've moved this methyl up to the top here. Okay. I don't know much about that chemistry. Maybe that's what this thing here is for the elimination part. I'm not 100% sure. Organic chemistry, as I've probably said before, not my strong suit. But anyway, moving on, we now have this. All right, so we then are going to add on. So I'm adding on plus N2 H2. All right, which is the kind of reaction I really do not like. Okay. So I had to look this one up. So this step here involves a ketone plus hydrazine. If you want to see more information about it, it seems to be a pretty standard reaction, and all that happens is you replace the ketone with the hydrazine, and you get that. And then I double check the molecular formula: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, and the N2. All right, so we're okay there. Again, sorry about that one. I don't really know much about that kind of chemistry, but if you want to look it up, it's a ketone plus hydrazine. Right, carrying on. So for that, I mean, that's 6 marks, right? I feel, number 1, you definitely get that one. Okay, number 2, if you've been paying attention, you should be able to get that one. This one is a little bit tricky because I feel like the enol reaction, the initial enol reaction is fine, but then there's that extra elimination makes that one a little bit tricky. And this one, if you know it, you know it. If you don't worry about it too much. Okay. Tick which steps involve enolate chemistry in the answer booklet. So where did I use enolate chemistry? I didn't use it to make this. I did use it to make this, remember here. So step 2, yeah, that used enolate chemistry. Here, yes, I used it there when I did this. So step 3, that used enolate chemistry, and then step 4 was to make this, which is something else, so I don't know what that is. So step 2 and step 3, use enolate chemistry. And then, so let me move on. The production of syntin was halted due to high expense, and then they wanted to use bacteria. So there are 4 types of reactions. Tick the reaction type catalyzed by enzyme 2. Enzyme 2. So don't get freaked out by this thing here. That just means it's bonded to something else. I don't know. Like, I'm not a biochemistry expert. Maybe it's bonded to, I don't know, a longer carbon chain, or I don't know, some biological thing or something. Anyway, it doesn't matter. Just look at the bit that we're given. So the only difference here is the ketone becomes an alcohol. That's all it is. So it's obviously reduction. Simple as that. Okay, no need to worry about it. I mean, we can look at the others. Obviously, it's not. If it's a reduction, it's obviously not oxidation. Condensation, no, there's no removal of water or anything like that. Hydrolysis, we're not splitting up anything. Isomerization, no, because the molecular formula changes. And elimination, no, it's not an elimination reaction. Identify the other products X and Y of enzyme 3. So we have this reacts with this to give me this, and then my X and Y. Okay, so well, we can just treat this as a normal chemical reaction and ignore these things here, because I've got one thing that X things is bonded to, two X things is bonded to, and I've got the two X things is bonded to here, so fine. And then I've got 1, 2, 3, 4, 5 carbons, and I've got 1, 2, 3, 4, not enough. So one of these must have carbon in it. All right. Then I can see that. So that's my first piece of evidence. Then here I've got sulfur bonded to my squiggly thing, sulfur bonded to my squiggly thing, sulfur bonded to my squiggly thing. Oof. So this is probably going to be sulfur, which means this is probably going to be carbon. Then oxygens. Well, I've got 2 oxygens here, and I've got 1, 2, 3, 4 oxygens here. All right. So at this point, if you haven't at this point thought CO2, you're probably not thinking hard enough. All right. And then I can count up my hydrogens. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 6. Okay, so X is CO2, and that is SH, because you wouldn't want to have just the S by itself. And then this is a really nice question. How many marks do you get? You get 2 marks for this, very generous. So the synthesis of fumaromycin A begins in the following way. For each sequence, each enzyme is required exactly once. Complete the table in the answer bucket to give the order of the enzymes required. All right, so this kind of question, very nice. You think about it for 30 seconds, and once you've thought about it, it becomes very, very easy. So that's my final product. Okay, which has the cyclopropane ring in it. No ring, no ring, no ring, ring. Okay, so it's a good bet that enzyme 1 is going to be the last one. Okay, now in order to make the ring, I need the double bond. Where do I get my double bond? I get that from enzyme number 4. So you can see what happens is, in order to get this, I first make it with the double bond, then I get the ring. So, oops, 4 is that. Okay. Then, in order to get the double bond, I need the alcohol. All right. Which one gives me the alcohol? Enzyme 2 gives me the alcohol. All right. There's no alcohol here, so it must be 2. And each one is used once, so that must be 3. So you can see enzyme 3 gives me the 2 ketones, enzyme 2 turns a ketone into an alcohol, enzyme 4 turns the alcohol into a double bond, and enzyme 1 turns the double bond into the ring. And you are done.